show you how we basically incorporate the combustion and Dalby change during the combustion and also during stage they find the enthalpy. Okay, so we look at this question again. So liquid propane C3H8 enters the combustion chamber at 25 degrees Celsius at a rate of 0.05 kilogram per minute, where it is mixed and burnt with 50% excess air. So we are told that we have 50% excess air. An analysis of the combustion those gases reveals that all the hydrogen in the fuel burns to CO2, but only 90% of the carbon burns to CO2 and remaining 10% forms CO. If the exit temperature of the combustion gases is 1500 Kelvin, determine the mass flow rate of the air and also the rate of heat transfer from the combustion chamber. Okay, so we need to find the mass flow rate of the air and also Q, these two things. Okay, so now, first thing, here we know the output of the gases here. We know that you get H2O, you get CO2, CO, O2, and N2. You are also told that CO2 and CO are split into 90 and 10. So technically speaking, I think this one you can just solve, directly, but usually I don't encourage this kind of method. So what do I mean by that? Let's talk about this first. So you are told that you have 50% excess A. Okay, but how much is 50% excess A? And then how do you find that? So now, so usually, right, this is a step in combustion that usually I will encourage. So whatever so sometimes it is not a must, meaning you can still solve without doing this. But most of the time I encourage is this. So regardless of what the question tells you. So like in this question, they tell you you have 50% excess A, so you have extra air. Exit you have CO, meaning this is an incomplete combustion. We don't construct a chemical equation based on this first. What we do is we try to find what is the theoretical A, or we find what is the stoichiometric A first. So how do we do that? So you assume complete combustion first. So like in this case, we assume we assume complete combustion with no excess A. So at the exit, so this one we assume stoichiometric combustion as A. So you assume that at exit that you have a complete combustion, there is no excess air. So if the general case, the most ideal case, no extra air, exact amount, complete combustion, you will always get CO2, H2O, and 2. Just like this one. So from here, you find out what is the stoichiometric amount first, or the theoretical A. So based on this, so it means that for every mole of the fuel, you will need 5 mole of oxygen. 5 of the total air is needed. So this is what this question is trying to say. So from here, then yeah, so you know 50% excess air, right? So you know 50% excess air, that will mean the actual air that you have is 7.5. Let's go, 50% extra. So this question, technically speaking, you don't really need to do the first step. You can still get this 7.5 on if you balance. But again, what I encourage is to just start from this one first, safer, because that it doesn't work all the time if you don't go to the stoichiometric first. Okay, so 50% excess air, so the air you have 7.5. Output, we know that H 100% is converted into H2O. So we have 8H here, meaning H2O, we have 4. As for the carbon, you are told that 90% of the carbon goes to CO2, 10% goes to CO. So originally you have 3 carbons. So 3 carbon 90%, 2.7 goes to CO2, 0.3 goes to CO. So then from here, whatever that is left over, so you need to balance a bit. Here we skip the balancing step. But so whatever that is left over from the oxygen is the extra oxygen. Then nitrogen, as usual, is just 3.76 times 7.5. So based on this, then you can calculate the FU ratio, as you can see here, 7.5 multiplied by 4.76, 29 fixed step. And then at the bottom is the mass of the fuel. So from here, you can get the FU ratio. So why do we find the FU ratio? Because the question asks for the mass flow rate of the air. So then, based on the mass flow rate of the air given by the fuel given by the question, you use the FU ratio, you can get the mass flow rate of the air. So part A, is everyone clear on what's happening here? So like I mentioned yesterday, the constructed equation part is more important. The enthalpy calculation one will ask as much compared to the other one. So the more important one is you need to know the chemical equation part. Okay, so B, the heat transfer for this steady flow combustion process. So we need to calculate how much Q out is this case. So we need to apply this equation that was shown just now. So the equation just now, sorry, not just now, yesterday. So we show you that we actually need to have this equation to calculate the enthalpy change physically. This one is from the chemical reaction. So the formation one is the chemical reaction, while this one is based on the change in the state. So how do we make use of this? Actually, it's just very tedious. The values are all there. So this table has to be given to you, like in this case, we give you this table. So you can see here, for each of the, so based on the tedious part is this, you need to base it on this equation. So this is the reactant, these are the products. So everything is involved here. Then, so this will be the each of the individual mole, because we calculated each of their mole just now. Okay, so then reactant, based on here, you can see so at the reactant part, it will be 25 degrees Celsius, so it will be the 298 Kelvin. So this will be the 298 Kelvin multiplied minus the 280. So let's go to the next one, easier to see first. It will look very confusing now because very long. So very tedious, but we look at the equations slowly. So the first one was the reactant. Reactant was C3H8 with air, right? So for the C3H8 part, so you see we have 1 kilomole of C3H8. This is the HF. So we come back here. Let's see. This is the HF. So this term. Then, but of course, for C3H8, the rest we don't have any value here. So here, this is supposed to be a 2 because it's 298 minus 298 because we assume that. So we go back to the question first. Because the question says something, let's look for it. It enters at 25 degrees Celsius. So 25 degrees Celsius is actually our reference temperature. So this is originally the temperature. So now, this degree thing, the one with this degree sign is the reference point. So C3H8 enters at the reference point already. So meaning there's no change in the state of C3H8. That's why the first one, there's nothing here. That's why we write C298 minus 298 because this is the reference. So this one's nothing. You can just take off. Then the next reactant, next one is oxygen, right? So oxygen and nitrogen, we learned previously, the enthalpy of formation is 0. There is no enthalpy of formation. So here is 0. Then you look at the value here. So now oxygen, so the air enters at 7 degrees Celsius. And the combustion will take place at 25 degrees Celsius. So that's the change of the state. So oxygen and nitrogen, you can see this is at 7 degrees Celsius, this is the enthalpy. At 25 degrees Celsius, this is the enthalpy. So, which is fine. So this 7 degree minus 25. So 7 degree minus 25. Change in the state. So once again, the first one is always the first one is the formation enthalpy. This one is what you usually do, the change in the state. So from 1 degree Celsius to 1 degree Celsius. So this is from 7 to 25. So these are all so these three are the reactants. So you can see we total them up. Then these are the products. So product also same thing. So you look back at the product. So we look back at the equation first. So the first product is CO2, right?
Okay.
And we have 2.7 kilomole. So you can see CO2, 2.7 kilomole of CO2. Then HF of the CO2, 393. So this is the one. Then once again, same thing, the change in the temperature from 25 degrees Celsius. So CO2 exceed is 1500 Kelvin. So we take the value from 1500 Kelvin here, which is 71,000. Then this is the one. Then minus, again, reference is always 25 degrees Celsius. So we minus the reference one, which is 9364. So this one. So you repeat and do for all of them. So this part technically is not so that complicated, but the problem is it's very tedious because you keep repeating the same thing. So for CO, also same thing. You use 0.3 kilomole, you use the formation, enthalpy at 1500 Kelvin, 25 degrees Celsius. Let's look back at this equation, okay? Just this equation, you just need to remember this equation. So this is the reactant and product. Reactant and product. So reactant left hand side of the equation, product right hand side of the equation. This one, enthalpy of formation. This one also. Okay, so enthalpy of formation. You just need to choose the HF value. This is the reference temperature enthalpy. So reference is always 25 degrees Celsius, which means we are taking all these values. This is the enthalpy at the temperature. So whatever temperature that the thing is at. So for C3HN is 25, so we don't need to do anything because it's 25 minus 25. For the air, is 7 degrees Celsius. So you take this value. Product 1500 Kelvin. Okay, product is 1500. So for the product, you take these values. So that's all. So basically, this whole equation, right? So we go back to the slide first. Pretty much this whole equation is this. It is exactly what is written there in the black part. So this is basically the enthalpy from the chemical reaction. That's why we call it the enthalpy of formation, meaning how much enthalpy or heat is released when you form this particle. That's from the chemical one. Then the sensible enthalpy is relative to 25 degrees Celsius is basically the enthalpy of the product or whatever of the elements at that temperature relative to 25 degrees Celsius. So if it is at 10 degrees Celsius, then it is enthalpy at 10 minus 25. If it is at 100 degrees Celsius, then it's enthalpy at 100 minus 25. So this question actually, even if it comes out, it won't be too hard. Because that table that I showed you just now, I don't think it is actually in the table that I need to give you. The table that I give you will have enthalpy of formation, but not the other three, I think. So either way, I still need to give you this separately. You just need to know which value to take. Plug in. So it's very tedious, basically. You need to do all these things. So the product here will give you kilojoule per kilomole. So for every kilomole of C3H8, this combustion, for every kilomole of C3H8, it will release 63880 kilojoule. So thus, 363,880 kilojoule of heat is transferred from the combustion chamber for each kilomole of propane, or for every 44 kg of propane, because 1 kilomole of propane is 44 kg. So this corresponds to, so if you want to find the heat loss for every kg, then you divide by 44, because that's the molar mass of propane. So why do we do this? Because we want to find the mass flow rate. So then the rate of heat transfer for mass flow rate, so you not divide mass flow rate, but you want to find the actual heat transfer. So then you multiply this with the mass transfer of the fuel, then you get the heat transfer in terms of kilowatts. So basically this is in kilomole, you convert it to per kg, then you multiply by mass flow rate just like usual. This looks very confusing at first one, but you try to look at the notes again, you compare the table value and what is written here, you can make sense of it. Okay, so now okay, we look at example 1. This example actually is quite complicated. But okay, I don't have this example in unit SI, there's no choice in real image. I pretty much you don't need to, I'm not gonna ask you to do it in unit exam. I just want to show you this form calculation. Alright, so the constant volume tank contains, think of it as just 1 mole, okay? So 1 mole of methane gas and 3 mole of oxygen at 77 degree F and 180. The contents of the tanks are ignited and the methane gas burns completely. So if the final temperature is 1800 R, determine the final pressure in the tank and the heat transfer during this process. So before and after, so this is actually still a standard combustion. But when you are facing with closed system combustion like this, then something is slightly different. The air, or rather the oxygen, is already inside this tank. So meaning, right, when you, let's say if you try to do a chemical equation, in this case, you don't need nitrogen. Because you are not taking air from outside. They explode inside. So inside there is only oxygen, so there's no nitrogen in this case. Okay, that is if you are to. So let's look at the calculation here. So again, like I said, ignore the unit. As long as you know F and R is for temperature, and the pound mole is molar. That's about it. Okay, so anyone here doesn't know both degree F and R is for carbonic temperature? Degree F is the counterpart for degree Celsius. R is the counterpart for Kelvin. It's the same thing. But of course, again, I said I won't ask you to do this like that. Just like, so happen this example I cannot get really aside. Okay, so we have our typical assumption. So you can see here, for this case, the chemical equation, we only have CH4, O2. Okay, because this is a tank. Inside the tank, there is only O2. We don't have N2. So the product, if you assume complete combustion, then it's just CO2, H2O. In this case, it's not complete combustion. So they tell you that the acid will have O2. But this case, you don't need to balance it. Why? Because you already know the actual number of mole of the oxygen and CH4 from the start. Because they tell you what are the mole. So you don't need to balance it based on the stoichiometric equation anymore. You just need to balance it based on the output. So we have CO2, H2O, and O2. So this one, let's say, if you have to balance this lah. So C, you know that. On the left is 1, on the right, let's say we call this X, Y, Z. Then you know this is X. Balance with H. So on the left you have 4, on the right you have 2Y. So Y equals to 2. Then we balance the O. So on the left we have 3O, on the right we have 2X. Oh, sorry. We have. So this is a commonly made mistake. We have 6O here. So we have X, 2X, and then Y plus 2Z. So then you balance this, you get Z equals to 1. So that's how you get all the value on the right. So again, in this case, we don't need to do a start with stoichiometric equation because the left hand side is given. The amount of oxygen is given to you, so you don't need to find what happened in the ideal case. Okay, so now we look back at the first the question. Part A asks for you to look for the final pressure of the tank. Very straightforward. If you don't know what to do, ideal gas equation. So here they use ideal gas equation to find out what is the final product pressure. Because you know the initial pressure, you know the initial temperature, you know the initial volume. So we don't know volume for both sides, but we know volume should be constant. That's why, so they just replace the volume and then they just balance it out. Actually, this one is just PV over T equals to PV over T. Can you do that? No, we cannot do PV over T equals to PV over T because mole is not the same on both sides. So, but yeah, you can use RU, you have N from both sides now. T you also have, it's just that you need to convert it to R. If it is degree Celsius, then you need to convert it to Kelvin. That's pretty much it. Same thing. So you can see the volume is constant. So they are just equating volume equals to volume. You can split into two, you can find volume first and put it in the second equation. Same thing. And then, so if this is in degree Celsius and Kelvin, it's just inside, right? Just same thing. Okay, so now we look at how much heat is being released during this combustion. So pretty much if you explode this bomb, how much heat will be released. So this is a closed system. So rather than using the previous equation just now, since this is a closed system, we have an additional PV term here, as I showed you yesterday. So the new QR equation will have this additional term. And we also show you that because PV is a bit hard, we use ideal gas equation to replace the term. They change into RUT instead. Change the PV to RUT. And RUT is easier. The temperature we have, RU we also have. Because the previous one, technically you can also use that, but then B is a bit hard to find. Then the rest is the same. So here, you can see at the reactant, we took out the entire H minus H because the reactant itself is at the reference state. So for imperial unit, 77 degree F or 537R, they are the reference state. So meaning even if this part we write how this, it will just be H77F minus H77F. So they cancel. So here we just took it out to make it look simpler. Then the rest you can see the equation is exactly the same with the addition of IUT. That's all. So again, same thing. So reactant CH4, you put this, and also O2 is 0. Then at the product, then will be CO2, H2O, then O2 with the respective temperature. So it will be final temperature 1800 minus the reference. So this will be 25 degrees Celsius in SI units. Then for each of them, you need to minus the IUT. So this IUT is based on the reactant IUT, which is the 77F or 537R. This T will be 1800R. So then you can see from here. So CH4 formation, and then RUT. So RU for, this is the RU for imperial units. That's all. So you can see here, so this is RUT. Then oxygen there's no formation, so it's 0. Then again, same thing, RUT minus. After that, for the product, then same thing, CO2, then you do at each of them, then with the RT, each of them for the RT. So once again, it looks complicated already, but it is actually not too hard, because all you need to do is plug the value from the table, but you need to understand the equation. Okay, so we still have a little bit of time. Let's look at one example from the next slide. Okay, so now this type of question is a little bit more common for your exam compared to what you saw just now. But sometimes I still play around with that. You do a few past year, then you need to see I do like a few. Okay, so this first example I will show you the following one. For our following class, I will ask you to try. Okay, so here, oh yeah, for following class, so our replacement class is next Thursday, 4 to 6. Should be in your timetable. Okay, no choice. That's the only time.
This week no replacement, right?
Not this week, no. My Thursday is off on Thursday. This week let me rest one. Next week we have Monday, Tuesday off, so yeah, and Thursday. Okay, so you have a sample of this with following composition. So, what kind of fuel is this? This is a solid fuel, okay, a coal. So only solid fuel will be given in this form. Alright, so you get a solid fuel here. The first question asks you to calculate the stoichiometric air-fuel ratio. So then the second question asks you to calculate the air-fuel ratio and the dry and wet analysis of the product when 20% excess air is supplied. Alright, so like I said, I will show you how to do this first one. The